Hey everybody, this is the density demo we're going to talk about in case you missed in class or you just want to revisit the ideas. So here we go. We started with what density is, and as a class it sounded like we decided that it was how much mass, how much weight is smashed into a certain space. Okay, so to kind of give you an idea, what we talked about in class was this empty soda can versus this crushed soda can has a different density. Now this one is less dense because the amount of aluminum is spread out over a greater area. And this one, we've smashed more aluminum into a smaller space. Okay? So then we had the conversation about, well, what if we have two soda cans with equal volume, or even three soda cans with the same volume, right? These are all 12-ounce cans. How could we decide or determine if one is more dense than the other? And then one of you decided, like, we should maybe all float it in water and see what happens. So what I have is two jars filled with equal amount of solution, and we've basically just floated them in the solution. So we made predictions about what's going to happen if we put the Mountain Dew in this one versus this one, and most of you said it was the same thing. It's going to float or it's going to sink. And then we did it, and people cheered, and it was very exciting. And then we moved it over to this side. We made the observation that it, in fact, doesn't float. Okay? So just for a moment, let's talk about this one right here. As a class, we decided that there must be more Mountain Dew in here, making it heavier than the water. So then the idea of density was thrown around, and it being more dense than the water, and everybody seemed to agree with that. So then what we did was we made some predictions about the Pepsi, and we put the Pepsi in, and the Pepsi kinda does the same thing, but it floats, and then it sinks. And so we had a conversation about why the Mountain Dew seemed to sink faster than the Pepsi. And then we tried the third soda can, and everyone made the prediction of it sinking or floating, and everyone said, well, it's 12 ounces, just like the other ones, so it's going to sink too. But then this happened. So we then had the conversation about, well, why does one float, and why does one sort of bobble, and why does one sink? They're all the same amount of soda, so what is it that's different about these three cans? Well, we took a snapshot of the ingredients, and you can find those posted on that Schoology page. But real quick, for a direct abstract between the two, we'll leave this Pepsi, the middle one, kind of out. You can get a clear picture of sodium and sugar. Okay, and so then everybody decided, whoa, the Mountain Dew has more in it, and that's why it sinks, and this has less in it, and that's why it sinks. Well, the idea is both of these are 12 fluid ounces, and then I don't remember who it was, but somebody said, oh, the Mountain Dew's a better deal because you get more stuff sort of smashed into here, and then the connection was made, well, this must be more dense because we've packed more sugar, more sodium, more, just seems like everything into the Mountain Dew, which makes it more dense than the water, and also more dense than the Diet Pepsi. And then somebody did bring up the question, well, are the soda cans, do they weigh the same? So then we took some empty soda cans, and we weighed them, and found that an empty soda can weighs somewhere around, I think it was like 12, 13 grams, right, somewhere around there. And then we even tried weighing the crushed one, and whether it's crushed or uncrushed, it's still the same amount of aluminum. So we kind of took the idea of the cans weighing different amounts and threw that out, and it seems like we are all in agreement that it has to do with how much is packed into the 12-ounce soda can. So the idea was that the Mountain Dew has more stuff in it. It's more compact, therefore it's more dense than the Diet Pepsi. But it's also more dense than the water right in here, which means that it displaces or pushes away all of the less dense stuff, allowing it to sink down to the bottom. Now, when we went to the other jar, a lot of people were kind of upset and they said, Mr. Buzov, that's not fair. What's in this? And why is he doing that? And so I said, well, just kind of connect the idea of why the Mountain Dew sank in the other jar versus this jar. What could we infer, what could we assume about the solution in this jar? And somebody raised their hand and said, well, Mr. Buzov, this has to have more in it than the Mountain Dew because it is holding the Mountain Dew up. And then we basically came to the idea that the Mountain Dew is less dense than whatever's in this jar. I put about 200 milligrams of salt in here, boiled it up, super saturated it so the water wasn't holding any more salt, and it basically made the water, I snuck salt into it so that there's actually so much salt in this water that there's no room for the Mountain Dew to go all the way down. Now, kind of the neat thing, and we talked about, the Dead Sea versus Lake Michigan, and how the Dead Sea is one of the saltiest bodies of water on Earth, and how, because it's so dense, it holds people up a little bit higher than regular water, is you can actually kind of see that with regular water and super saturated salt water, right? Actually, it's so much more dense that all that extra salt is basically saying there's no room for you in here, and we're going to make sure that we can push you up as high as we possibly can, making that Diet Pepsi float a little bit higher than in regular water. So the main idea is from that demo is to think about how density plays a role in how air behaves. So if it's warm, are those air molecules kind of fitting close together, or are they bouncing around and taking up more space? And how does that make it either more dense or less dense? And the same thing with cold air, is if the cold air, if those molecules, those air molecules, are more compact, does that make the air heavier or does it make it lighter? And that directly connects with our lesson objectives from Chapter 4 of how does the surface temperature affect air movement, and then also how does the surface temperature actually just even affect the air density. So if you can, try and think about how dense salt water connects to maybe a dense air mass and what that would do for the movement when one cold air mass smashes into another warmer air mass. Try and think about the arrangement of those two things. Thanks for watching the demo, and happy science.